Hi there, this is Tina for EE308 Fall 2012, and this is the video for the homework and I guess the Thanksgiving break. First we're going to go over just a few things since we started frequency response so long ago. We'll go over a few of the background things, but I won't spend much time on any one of them. But then when we get to kind of the newer stuff, I'll slow down. Okay. So these slides mostly follow what is posted. I took out some of those slides just because you can read them on your own time. There's mostly on things that you already covered the week before Thanksgiving. Okay, so frequency response, just to remind you what frequency response is. Every circuit has R's, L's, and C's in them. I hope you can hear me over my birds. And those R's, L's, and C's combine to make low-pass filters and high-pass filters. And that is what frequency response is. It's how those low-pass filters and high-pass filters affect your circuit's behavior. And of course, a low-pass filter will let the low-frequency signals through and not let the high-frequency signals through, so your amplitude will die at some frequency. The high-pass filters will give you low-frequency zeros, so you don't see amplitude at lower frequencies, but then it increases. And just to kind of tie that in with what you've seen from time domain. Time domain, if you have, say you have a charged up capacitor and you discharge it through a resistor, you get something like this. At first there's a big voltage across the resistor, so lots of current flows so that the voltage changes kind of quickly. But then as the voltage across the resistor gets smaller and smaller and smaller, the current drops, and as a result of that, the voltage drop across the capacitor slows down. Okay, and if you have a big capacitor, it takes longer for it to discharge. If you have a smaller capacitor or a smaller resistor, so you get more current, it takes a short time to discharge. If you go over and look at the frequency response, your Bode plot, you have a point where this 1 over RC, that corner frequency, we're looking at a low-pass filter now. That 1 over RC, your amplitude starts to drop. And if you have a small RC, remember this corner is 1 over RC, so if RC is small, that number is big. So if you have a small RC, it can go to higher frequencies. If you look over here, the smaller RC means it responds quicker. Okay. When something responds quicker, or there's a sharp edge, for example, if you have a circuit that has a square wave on it, this is a fast transition right here. Let's see if I can find red. This is a fast transition right here. Fast transition means there's a high frequency component to that signal. Okay. So going back over here, this transition's fast. That means that you're going to have a pole that's farther out this way. Oh goodness, the birds are really enjoying this too, I think. Okay, and if you look at that, if you look at this at the circuit level, you give it some sine wave, and sine wave comes out. You can keep going up to a certain frequency and you'll still get the same amplitude out, but at some frequency you're gonna see the amplitude drop. Okay, you say, oh, big deal, so I have a little RCs in there, you know, who really cares? I took a 555 timer and I just kind of looked through it and kind of circled the points that I think, you know, would have a pole at them, and I came up with those. So yeah, it's all over your circuit. And you can, the analysis that I'm going to show you, you can look at each individual node. You can come up with an R for that node and a C for that node and figure out where that pole is. And you can do that for this entire circuit. sounds really painful to me. So what you usually do is you look at your signal path. It's a signal path that's going to be affected. If there's capacitance on the supply or on ground, that's actually a good thing because it's going to quiet it. But along the signal path, so here's your VN, here's another VN, goes out here. Anything along this path, so here's your VN. Anything along this path, here's another common source amplifier. Anything along this path, where there's an R and a C, that you probably want to be careful of. But again, all these circles up here on ground, on supply and ground, those don't really matter. Here's some biasing circuitry, I think. It doesn't look like it's diode connected, but if there's biasing circuitry in here someplace, that's a DC circuit. So if there's capacitance on that, you don't really care. That's actually a good thing. Okay, so review, just a quick thing. If you give a step response to an RC circuit here, a low-pass filter, and when you give it enough time, it goes up to that maximum, whatever amplitude the input was. But if you keep speeding up, and speeding it up, pretty soon you get to a frequency where this doesn't have time to discharge back down or charge back up, and you lose your signal. So a low-pass filter is you're basically not giving the capacitor time to charge and discharge. Okay. And you've done the math in 211, I believe, where you had the differential equation, you solved it, and you saw that you got this e to the minus t over RC. Okay, that's your time domain equation. Okay, for a high-pass filter, you think, okay, so that last argument, the capacitor doesn't have time to charge or discharge. That makes sense for the low-pass filter. For the high-pass filter, what happens is that the voltage across the capacitor can't change instantaneously. So if you change one side real quickly, the other side changes quickly, and then it discharges through your resistor. Okay, so initially this node, if you change this voltage, initially this node goes up too, and then it discharges out the resistor. So that's what's happening here. And if you notice here, the majority of, so here's V in, the majority of V in is almost at 0 here. So this is for a low frequency input, and this is supposed to be V in. Okay, if you give it enough time, it goes back down to 0. But if you speed it up, pretty soon you get an output that looks kind of like the input. You're just not giving it time to discharge. So low-pass filter is you're not giving the capacitor time to charge and discharge. For a high-pass filter, you're not giving it time to discharge, I guess. Okay, and filters do good things. Anybody doing stuff with audio or communications or anything like that, and those filters are really important. Anybody that's trying to get rid of 60 gigahertz noise or high frequency noise that you get just in using breadboards and all that, that filters can do good. Huey, Gabby, Scotty, thank you. Okay, and those results mentioned in class, the Bode plots, the only reason people use Bode plots is that they give you lines for exponentials. You saw when you solved the equation for an RC circuit, you got that e to the minus t over RC. That is hard for a human to look at. It's hard for a human to look at a line and say, yes, that's an exponential. It's hard for you to say, oh, yeah, that looks like an exponential, but is it really? You don't know. But if you put it on a log plot, now it's a line. And humans understand lines. We can detect whether something's a line or not. You just can't really tell if this fits e to the minus t over RC. Okay. Okay, so Bode plots, and I put in some slides about Bode plots. I'll let you look at them. The one thing I'll say here is that when you find magnitude, so one of the plots you do on Bode plots is magnitude, one is phase. For magnitude, you multiply if you have a 1 over, say, 1 plus j omega RC, this is where you're going to have one of your poles. When you want to find the magnitude, you multiply that by its complex conjugate and then take the square root of the result of that. Okay, and we'll just do this slide. Okay, so when we have this equation right here, here's our magnitude. We've multiplied it by the complex conjugate, and we're taking the square root of it. Okay, when omega is really small, then this term disappears, and you have 1 over 1. The square root of 1 over 1 is 1. When omega equals 1 over RC, now you've got 1 over the square root of 2, and that's your minus 3 dB. Okay, so when your frequency is right at your pole, 1 over RC, that gives you 1 over 2, square root of 1 over 2, 1 over the square root of 2, and if you take the log of that, you get your minus 3 dB. Okay, if omega is really large, now this term dominates, and this term becomes bigger than 1, and the equation that you work with is your 1 over omega RC. Okay. And we can keep going, but I'll let you look at these slides. And I put up slides with animations so you can play with these if you want. One comment is if you had 2 filters and you could put an ideal perfect buffer in here, one that has an infinite Rn and no capacitance on the input, so no Cin, or and Rn equals infinity, and output R out equals 0, and perfect voltage amplification so a gain of 1. If you had a perfect buffer like that, what you'd have is you'd multiply the gains of these two, and each one has 1 over 1 plus j omega RC. This is R1C1, and this is R2C2. So here's the gains for the filter. Since they're in series, you multiply them. And remember, when you multiply numbers and then take the log, it's actually the sum. So if you have log of A times B, that's the same of log of A plus log of B. And that's why you can treat each one of these separately, treat the effects of each one separately. Okay, we'll flip through that. We'll let you play with those. Okay, phase response. There's another thing that you like to plot with Bode plots. Polar coordinates, you take the arctan of the imaginary part of your number over the real part of your number. So if you had 1 plus j omega RC, the imaginary part is that j omega RC. So omega RC, and this would be 1. And that's how. And then you take the arctan of that to find your phase difference. And what you end up with is one signal either leading or lagging the other signal. Okay, we talked about having that second pole and the minus 180 degrees phase shift. That's in relationship to when you're using feedback. All of your amplifiers that you've used so far, they've used negative feedback. If you have 180 phase shift now, what used to be negative feedback is now flipped over and it's positive feedback. And the rule that we're using in this class, we're talking about Barkhausen's. And Barkhausen says if you have an amplifier with feedback, that's the important thing. It doesn't matter. If it doesn't have feedback, this doesn't matter. But if it has feedback at 180 degrees plus or minus, if the amplitude, the output of your amplifier, if the amplitude of that or the gain of that is greater than 1, in other words greater than 0 dB, then your circuit can be unstable. And in general, you don't like to be at 180. You like to be back, 30, 60, 45 degrees here, and then you don't get such a big effect from that positive feedback. Okay, in this case right here, I have this starting at 0 dB. That's because filters give you the same output as input. So if you have an input of 2 volts peak to peak, your output will be 2 volts peak to peak if it's letting the signal through. And then if you put V out over V in, you get 1. So for filters, your top line is 0 dB. But for amplifiers, if you put V out over V in, now you get the gain. So you get, for example, for a common emitter, you get GM R out. And so this would be 20 log of GM R out. But this is for a filter right here, this 0 dB, only for a filter. Again, for an amplifier, this would be 20 log of whatever your gain is, which again for a common emitter is GM minus GM. Don't want to do that. GM R out, absolute value of your gain. Okay, and just there's basic rules, but one thing here. Oh, I forgot to check this. This right-hand plane 0, I have to check that because I found 2 different sources online and they're saying different things. As I remember it, it makes your phase worse, but starts to increase your gain again. So it does bad things. Remember on our plot over here, if we drop to 180 degrees, we want our amplitude to be less than 1, our gain to be less than 1. If you have a 0, a right-hand plane 0, as I remember it, so I have to check, the phase continues dropping, so it continues towards 180 degree phase shift, but it flattens this out. It brings your gain back up by 20 dB per decade. So it keeps the gain from dropping at the same time it's getting closer to that 180 degree phase shift. So right-hand plane poles, those are bad for feedback, as I remember. Okay, so I need to check that, but I just kind of listed up some rules here. And there's also complex poles and zeros, but we're not going to deal with them in this class. Okay. When we're on the, when you plot your solutions, let's say you come up with your transfer function and you have, 1 plus j omega RC, and then you have another one that's a quadratic. So there's a square term of omega in it. If you solve that and the solution is imaginary, then when you plot that solution, you aren't going to be on the x-axis anymore. Okay, so when you plot it on the imaginary plane, it's going to be off of the x-axis. We're only going to talk about solutions that are on the x-axis. No imaginary solutions for this class. High-pass filter, I just added this in to compare because we do see high-pass filters in our circuits too. High-pass filter, again, you just find the magnitude the same way, the phase the same way, but what happens with a high-pass filter is you end up with a 0 at frequency 0. So this starts and goes up. Okay, and so we talked about this in class, so I'm going to go fast through here too. When you do circuit analysis, you want to use the simplest model that will answer your question. So if we're working on a printed circuit board, say, and you're using a transistor as a switch, which means all you care about is whether it's conducting or not conducting, then you can model your circuit as a switch. You don't need to know about R's and C's. Okay? But what we're going to be, when we start to talk about frequency response, we had this other model, the small signal model. Let's see, let me just go, I cut out a bunch of slides right here. In between that last slide and this slide is that we've come up with the small signal model for low frequencies. That means it doesn't have any capacitors in it. But now we need to add the capacitors. And in the last homework, you calculated the capacitance of a MOSFET and a BJT. So hopefully you know where the capacitance comes from now. Okay. And there's 3 places you get capacitance, and we talked about those. There's the overlap, right here where it overlaps, and then there's the gate coupling to the channel. And if you're in cutoff or in linear, the gate couples to the entire channel. But if you're over here in active region, which is where we always are, the gate, the coupling right here, it couples to the electrons in the channel, but the electrons don't cover the whole channel, so you get this 2/3 COX WL. Okay, so we've done that. We talked about junction capacitance and sidewall capacitance. And then for BJTs, we've got these capacitors between the emitter base and the base collector and the collector substrate. So that's where we are there. So we had our original model, and we know that we have these three new capacitances: collector substrate, base collector, and base emitter. So now I need to add that to there. So here's our base emitter capacitance. Here's our base collector capacitance. And then you also have this collector substrate capacitance. Okay. And that's our new model for mid-frequencies. And I when I work it out, but I'm totally happy on exams if you write CBE or CBC. I might ask you what the official names are, because people will be looking for you to know those. And then here are the official names. Instead of CBC, CMU. And then instead of CBE, CPI. Okay. So these are the official names. These will make interviewers happy. Okay. So let's first go and say, all right, let's do a hand-wavy job and find capacitance at nodes. Okay, and this version 1, this is a partial lie. Okay, so all of the slides that I'm going to show you in the next few slides, those are partial lies, and then we'll get to the real story. Okay. But first, let's practice with our partial lie. And we are going to look at this node, I believe. Yeah, here's the node we're going to look at right here. And this is version 1, partial lie, partial lie, partial lie. Okay, we're looking at the capacitance at this node. And when you find, we're going to use the quick method here. When you're looking for the capacitance, if you're sitting on this wire, you have to go in all directions, not just forward, but you have to go back. And if you go back here, notice you run into wires that go up and down, so you have to go both up and down. So you have to go in all directions on this wire until you hit transistors. So here I hit a transistor, here I hit a transistor, and here I hit a transistor. Okay, and then here's your MOSFET. Oh, was the last one BJT? Yeah, okay, we'll go back and do that in a second. So if we're sitting here, let's say I go this way. What's the first one? 2? Okay. Let's say I go this way and up. So now I'm going to take care of M2. I'm sitting on the drain of M2. So if I go over here to my picture and sit on the drain, I look at what capacitors are connected to the drain. I see one to the substrate bulk and one to that overlap, that little overlap right there. So the capacitance I see at the drain is the gate drain overlap 2, and then the drain bulk right here, this capacitance right here. So that's what I see for M2. And then I go the other direction. Oh, I'm sitting on the drain again, so I go over here. Oh, I see drain bulk and I see drain overlap. So here's gate drain and drain bulk of 1. Okay, so that takes care of that. And then I go back over here. I'm sitting on the gate. So on the gate, I see 3 capacitances. I see gate source overlap, gate drain overlap, and gate to the channel. So gate drain overlap, gate source overlap, and then in textbooks, they won't call this gate channel, they will call it gate source. Because they look at that, let's go back over here. Too far back. If you notice, the electrons are kind of leaning over and up against the source right here. Since they're kind of leaning up against the source, they just call this source capacitance. It's channel. It's electrons in the channel that the gate's coupling to, but in your textbooks you'll see it called the gate source capacitance. So I'm treating the overlap capacitance. I'm treating the overlap capacitance and the gate quote unquote source capacitance different things. The gate source is the gate coupling to the electrons in the channel. Now, let's go back over here. So here's the node we're at. Same thing, you have to go in all directions. Say I go up to 2, I sit on the collector. So here I'm sitting on the collector. I look for all the capacitances that go from the collector to someplace. There's one here and one here. So the collector substrate and the collector base. So that's why I have the collector base and the collector substrate. And that takes care of Q2. I go down, I'm sitting on the collector again. So I look for what capacitance coming off the collector. Hey, it's a collector base, collector substrate. Then going over here, now I'm sitting on the base. So now I'm sitting on the base. I look at all the capacitances connected to the base. There's a base emitter and there's a base collector. So here's a base emitter, base collector. Okay, so that's the quick way to find the capacitances. And this is partial lie. Both of those are partial lies. So let's get the not lying version. And I'm going slower than I planned, so this video might be actually longer than an hour, longer than 50 minutes. Okay, so let's see. If the far side of a capacitor, so if I'm sitting here and I look at these capacitances, if the far side of the capacitor is connected to something that isn't moving, so if the far side of the capacitor is connected to something that isn't moving, then capacitance is whatever it is. So what I mean by that is, let's see, this substrate right here, it is generally tied to a DC voltage. It's not moving. So if I'm sitting on the source and I look at the source, the source bulk capacitance, I can look at that and say, if I'm sitting on the source, I see that the other side isn't moving. I can just say, oh, the other side's connected to ground. Okay, and if I do that, then I just use, in my calculations, I just use the value of SB. Okay, so that is, okay, so that's whatever this, and anything I say about MOSFETs is true about BJTs and the other way around. Okay, so any place here that you have a capacitance where the other side isn't moving, you just take that capacitance. So let's look at this. I have a collector substrate capacitance substrate that's tied to a DC value. So collector substrate, that's just whatever the value is. Okay, let's see. How about a collector base? The base comes off of the biasing circuitry, so that's DC too. So both of those are both connected to AC grounds, virtual grounds, and I just use the values of the capacitances. Okay, if I look down, I have a collector substrate. Okay, substrate tied to a DC value, so I just use that capacitance. But over here, I have a collector VN. VN's moving. This node is moving. So now both sides of that capacitor are moving. So that one's going to go with another rule. The other side, if I'm sitting here, the other side is also moving, so this rule doesn't work for that. Over here, I have a base emitter. Emitter is tied to ground, so I just use that capacitance. Over here, I have a base collector. Both sides of that capacitor are moving, so I have to do some special math with that. Anything that's tied to a DC on the other side, you just use that value. Okay, Miller capacitance. We did this in class, so I'm going to skip through the math and just go to the result. If you're sitting at the input of an amplifier, so here's an amplifier, here's a common emitter. If I'm sitting at the input of the amplifier and there's a capacitance from the input to the output, then what I can do is I can take that capacitor, remove it from the diagram, put it to ground, and use a new value of the capacitance that is, let's just go to here. Okay, so if I had this CBC over here, what I can do is I can get rid of it. I can take it away from there, and I can put it down here, but have a new value of 1 plus AV times your CBC. So whatever this original CBC, it gets multiplied by 1 plus AV. It's not just CBC anymore. Okay, that's one special capacitance. Okay, and then we had this other one over here where output's moving, input's moving. Got this capacitance. If you wanted to use the order of the terminals, it would be C, C, B. You're looking back this way. Okay. For this one, if the output moves, say 1 volt, the input is going to move 1 volt over the gain. Okay, so it's going to be much, much, much less. It's going to be 1 over the gain. In theory, if you have a gain of 100 or something, 1 over 100, that's like this isn't really moving. Okay. So what you can do, 3, okay, so if you're right here and you have this capacitance right here from the collector to the base, you can replace that with just CBC, because it's pretty much like this other side isn't moving, or you can do CBC times 1 plus 1 over AV. And I'll let you read through this if it's not clear where that comes from. Okay, so that's 2 things, or that's 3 things we've seen. If the other side is connected to ground, you just take the capacitance. If it's a Miller capacitor, in other words, from the input of an amplifier to the output of an amplifier, then you multiply it by your gain. If it's looking back into an amplifier, you just take the other side as it's connected to ground. Okay, let's look at another one. We looked at this one in class, so I'll make this explanation quick too. From VN, you've got a base collector capacitance, and this other side, it's not a DC value. It's floating. It moves according to. It helps Q2 accommodate different currents by moving, changing the VBE here. Okay, so let's say we move Vn up by delta V. If Vn moves up by delta V, this VBE, it's just changed by delta V. Okay. The emitter's tied to ground, so however much you move Vn is how much VBE changes. Okay, if you move that up delta V, that increases the current through Q1. Assume all of these are in forward active. That increases the current through Q1. If the current through Q1 increases, the current through Q2 increases. Okay, well Q2, now that current's increased through Q2, if this is in forward active, the way it's going to adjust its current, we may have a serenade in a moment. The way it's going to adjust its current is to change its VBE, but the base is fixed, so the only way it can change its VBE is by changing the emitter voltage. Okay, okay, so what happens here is if this goes up by delta V, this VBE has to change the same amount, and to do that, this is fixed, so now it has to move VE down by delta V. Okay, so Vn goes up by delta V, Vx goes down by delta V, and you get a net change of 2 delta V. Okay, so what that says is, right, if you had a capacitance there, you can remove it, put it down there, and your new value is 2 CBC. Okay, last one. We didn't cover this one in class. So this is the only one we didn't cover in class. If you have a follower, so here's your input, here's your output. The whole job of a follower is to have your V out move the same amount as your V in. And I use a transistor down here just to make it a little more ideal. Okay, so raise or lower V in, V out will move with it. Okay, you have a capacitor across here, the VBE. Now, if I move both sides of a capacitor, what is the net voltage change across that capacitor? Okay, if both ends of the capacitor are moving together, is there any voltage change across that capacitor? No. Okay, if there's no voltage change across a component in a circuit, that means there's no current going through it, which means you might as well just remove it from the circuit. And that's what you can do with a follower. If both sides of the capacitor are moving together, then that capacitor doesn't have any influence on your circuit. And what you get is, you had a capacitor here, you just remove it from your circuit. Okay, and I've only shown you one capacitor at a time, but all of these will have the VBE, the VBC, the VCSs, the CBEs, the CBCs, and the CCSs. I might have said VCB and stuff on in the explanation, but I meant C. Okay. Alright, so that's great. Now you can find the capacitances at the nodes without doing any small signal analysis. To find your the pole at a node, next you have to find the R. So here's your node. To find the R, you have to do the exact same thing you did with finding the C. You have to go in all directions until you hit a transistor. So here you hit a transistor. You're looking into the collector. That's RO. So that takes care of Q2. Then you go down, you see an RO, that takes care of Q1. Over here, you look at RN, that's R pi. And since all of these go to AC grounds, virtual grounds, they all go from this node to a virtual ground. These all end up in parallel, and you get your RO2, your RO1, and your R pi 3. Okay, and for MOSFETs, let's do the same thing. Go up, you see RO. Go down, you see RO. Over here, you see infinity. So I put those all in parallel, and you get the small signal R at that node. Okay, and to find your corner, all you do is you take that R and that C and put 1 over that, and that's your angular frequency for the pole. Okay, if you want frequency in hertz, just do 1 over 2 pi. Okay, and this is actually, I just noticed this right before I started the video, but so note this on your slides. The values that I have here are the line method. So you don't have your, what would it be? It would be the BC of 3. This needs to be multiplied by 1 plus AV. What the heck? 1 plus AV. Okay, and for the MOSFET, same thing. You've got and that should actually be absolute value. Okay, now it's not lying anymore, but now it doesn't fit on the slide. And then we can get rid of the lying method here. Yeah, I found a few typos as I went along, so I'll point those out. I have most of them in red in this presentation here. Okay, let's get back to the slideshow. Okay, and then so you have your R's and your C, and you can find your pole values. And note, and right here I just replaced AV with the gain. Since it's absolute value, I took the minus sign off the GM. So GM, RO1, RO2 in parallel. And this should have an R. No, this is the gain of your amplifier. It's not RO1. Oh, shoot. Okay, so this is a typo also. It should be 3-4 here. Yeah, it should be 3-4 right here. What the heck? Sorry. Real-time debugging. Okay. All right, so back to that. Okay. Yeah, and again that your time constant, C times your R, and your corners at 1 over your time constant. Okay, and if you have multiple amplifiers cascaded together, you know that if the gain of the first amplifier is A1 and the gain of the second amplifier is A2, and they're cascaded, in other words, the output of the first amplifier goes into the input of the second, then you multiply their gains. And that's just what you do here. You multiply their gains, including now the frequency response part of the gain. And you get this chain, you get your gains times all all the frequency effects on your gain. And again, reason why Bode plots are helpful is you see that if you have things that are multiplied together, if you take the log of that, you just add up the individual effect and get your final effect. I'm going to skip out on this one. Okay, well, let me just go through this part. Okay, so we're going to do small signal analysis. I'm going to go on to the next one. It's getting a little bit long. You can play with this. Here's an example of calculating the capacitance. I think that the C gate drain, I'm not sure if I multiplied that by year 1 plus AV on this one, so be careful of that. I need to go back and check that. Did I? Oh yes. Okay, so this is a new addition right here, and I just did it. Hey, sweetie. I just did it. Oakley. Oakley. Shh. Okay, I just did it on this equation. This is a typo on your slides. It doesn't. Your slides don't include this, so go ahead and add that into your slides. Okay, and then just an example of a calculation. I need to check if that 1 plus AV is actually in the calculations there. Okay, so next is small signal analysis. So we just did the quick method, and that's a great way to find poles, but it doesn't find zeros for you. So let's go through and find some zeros, or one anyway. Let's do the analysis of a common emitter. So you know, common emitter, here's your common emitter. It's got your DC, your biasing voltage, and then on top of that it's got the small moving signal, and then you have your VDD. Turn that into a small signal model. Means you replace the transistor with a small signal model. That's what I did here. Okay, but now, since we're going to be dealing with higher frequency stuff, we need to add in the capacitors. So we've got one here, that's your CBE, here's your CBC, and then we have the CCS to ground. Okay, you do the same thing. You zero DC sources, and then you after you zero DC sources, you can see that RC is in parallel with RO, all going to ground here. You can see that, what else can you see? I think that's about it. Okay, and your RO is in parallel with RC, which is also in parallel with CCS. Okay, and let's say we want to find R out. So if we want to find the gain of this thing, you want to find R out and GM again. So if you want to find R out, you zero the input. So here I've zeroed the input. If I zero the input, this goes away. Now I have, we have 0 volts on both sides of this capacitor. So you get to get rid of, this capacitor. You have 0 on this side, 0 on this side. If you look at R pi, it's the same thing. 0 on this side, 0 on this side. Okay. And now you have, you're sitting on your output. You want to, if we get rid of all this and redraw it, you come up with this. You have C mu going from this node to ground. You have CCS going from this node to ground. So I put them in parallel. This disappears and you have that resistor. So this is your resulting model. If you're finding R out, you have to look at the capacitors that are on that node and see what the other side is connected to. This one's connected to ground, so great. Okay, you go over this capacitor, oh, the other side is connected to ground, so oh, we don't have to do anything special. Okay, and then to find your R out, now you treat this as an impedance. You 1 over j omega. You have RO parallel RC, which is your original R out, in parallel with now this frequency dependent term. And it's just 1 over j omega. C mu plus CCS. So that's your R out. So let's find GM now. So this is GM, 1 out of 1. Okay. For GM, you zero your output. You short your output. That means there's 0 volts across CCS. means there's 0 volts across this resistor. So all of those go away. And this is what you end up with here. Okay. For GM, it's I out over VN. So let's come up with an equation for I out. For I out, you have this current coming through GM times VN. So it's the negative of that. And then you have the current coming across C mu. That current is whatever voltage is here minus the voltage here over the impedance of your C mu. So that's what it is. You have Vn minus 0 all over the impedance of that, which is 1 over j omega c. And you can see Gm equals negative Gm plus j omega c mu. Okay. To find your gain, you do Gm times R out. Here's your Gm. This whole thing right here is R out. And I left this as RO in parallel with RC. But let's see. Because this is our original R out, but now I'm going to put that in parallel with 1 over j omega times this C. And to do that, on top you get this times this. On the bottom you get this plus this. And then I just multiplied top and bottom by the j omega c mu plus c cs. And it comes out to this. Alright. Let's do one more step here. Let's factor a GM out of this. You say, well, there isn't a GM in that. Well, what can I say? I know where I want to go, so I'm going to divide by GM. So I pull out the GM. Here we have an RO in parallel with RC. And I pull that out front, and what's this? That's our original gain. That's our original gain. And then over here, we have all of the frequency-dependent stuff. So here's your original gain. And here's your frequency-dependent term of your gain. And just to make sure things are working out okay, and you could have done that up here, you could have done it any place, but at omega equals 0, that's as low frequency as you can get. At low frequency, you should get the same result as you did when you were working with the low frequency model. So if you put omega equals 0 in here, you have 1. This whole thing becomes 0 too. So you have 1 over 1. And you get your original gain back. Okay, the interesting thing you see here is, yes, we have a pole, and note that this is the exact same pole we got using that other method, where you just found the C at the node and the R at the node and multiplied them. It's the exact same result for your pole. Omega equals 1 over R naught in parallel with RC times your capacitance at that node. But we have a new thing up here, and this is a right-hand plane 0. And this will equal 0 when omega equals Gm over C mu. So let's formalize that. Gm over C mu. Okay. And that is your quick way to find a 0. The C mu is feedback, and it gives you your 0. And again, I have to check this. I saw this, just the multiple different definitions online. I need to go back and check my textbook when I have access to my textbook. But whenever you have say a common emitter, immediately you can say, oh, there's a 0 at Gm over C mu. And it's a right-hand plane 0. Okay, and your pole, that is, you just go over here, you find out what makes this term equal to 1. Get rid of the j. You find out what omega makes this term 1, and that is 1 over this whole thing right here. Okay. So there's your pole you found, and here's your 0. Okay, might as well go for all the characteristics. Let's find Rn. So for Rn, you can't short anything or open circuit anything. Well, I guess you do open circuit. You leave V out disconnected, and you want to find Rn. Okay, now you've got a problem. You go to all your capacitors again. You say, oh, is the far side connected to ground? Oh, yes. Okay. What about this capacitor? Oopsie, this capacitor, the far side is moving. Both sides are moving. So we got to do something with that. If you remember, this gets affected by the Miller effect. That's from the input of your amplifier to the output of your amplifier. So you can just use the Miller effect on this and change it to a capacitor of C mu times 1 plus AB. Alright, and then your Rin, since R goes to ground right here, none of this affects it at all. So this is your Rin right here, and you put, you have the impedance in this in parallel with the impedance of this in parallel with the impedance of that. And when you come out over here, you find your new impedance. Here's your old impedance, and here is the frequency response term. So you end up, just like you did with the other terms, if you zero your frequency, you get your original Rin back. Okay. So your pole right here is when omega equals 1 over all of this. And there's that right there. And you'll see that that is the same thing we found doing the fast method. Okay, things to note. Rin is not constant. It changes with frequency. So at a higher frequency, this is going to load the previous circuit more than at a low frequency. So the Rin drops as frequency increases, and you're going to get worse loading effects. So not only is your frequency being filtered, your loading is going to increase. Poles found were the same as those. Okay, yeah, poles found using small signal analysis were the same as those found using the fast way, where we found the capacitance and resistance at a node and just multiplied them. Okay, and you have a zero at GM over C mu. Okay, a couple more terms to define. Ft is where beta goes to 0, goes to 1. So in other words, IC over IB goes to 1. So let's do the math for that. Let's do a common emitter. It doesn't really have to be a common emitter. It could just be it can just be a transistor actually. That's I overdid this. We don't need this to be a common emitter. And what's nice is, since we're looking at IC, when you're looking at a current output, you just short it, and this goes away anyway. So the math is still the same, but actually what we should be looking at is just a single transistor. Okay, so we've got CCS, we've got our 3 capacitors. When you're trying to find beta, and this is an added thing. If it's in red, that means I forgot to put it on your slides. So you so you put in your capacitors, and you zero your DC sources. So here's 2 DC sources, so let's get rid of them. So these are just tied to ground now. If you're doing a current output, then again you ground it just like you did for GM. Remember, GM is I out, so you short the output. That is now you have ground on both sides of RC, so it disappears. So now we're basically doing the analysis of a single transistor. That gets rid of RO because there's ground on both sides, and that gets rid of CCS because there's ground on both sides. Okay, and here's our final circuit. Here's our simplified circuit. Okay, so there's our simplified circuit, and we want I out over I in. I'm going to, well, let's just set up the equation. I need one equation to get rid of Vn. I need Vn to turn into In, or IB. I out, IC is equals to negative I out, but let's find I out first. You've got your GM, negative GM VBE, and VBE is just Vn. And then on top of that, you have the current going through C mu. It doesn't really go through it, but how it's perceived, and that's the voltage across C mu divided by the impedance of C mu. Then you come up with a nice pretty term here. You could solve for Vn. Now you have Vn is equal to I out over this. I out equals negative IC, so you can plug that in. I just flip the signs on the denominator. Okay, so now you have an equation for Vn. Now I go back and you can figure out what IB is. The other side of C mu isn't moving, so you don't need to do anything. The other side of C pi is not moving, so you don't need to do anything special with that. Current in is the current through C pi, R pi, and C mu added together. So that's what these three terms are. Whenever there's a V in, you can replace that with this term and you get your IC. And you can go down and do the algebra and you get IC over IB equals this whole mess right here. Okay, I'll let you go through the algebra on your own. So here's that mess. If you put in 0 for omega, this term goes away and this term goes away. So IC over IB at low frequency is just GM times R pi. Okay, we haven't talked about that previous times, but if you think about this, this is R in, and right here GM is I out over V in. Okay, so GM equals I out over V in. Let's do this over here. So GM equals I out over V in, and then you're multiplying it by R in. Okay, here's V in. So R in over V in. If you do the math, that just equals I out over I in, which is what beta is. So all of this makes sense, which is good. Okay. So GM R pi, that's your R in, your beta, your low frequency beta, and then here's your frequency term. You always like to pull out the original value, the low frequency value. And if you don't know what the low frequency value is, when you get this messy equation right here, just to replace omega with 0, and that'll tell you what your low frequency value is. And you try to pull that out, and then you have your frequency term right here. And you can see again, hey, we've got a 0 at GM over C mu. That magic value keeps popping up. So this is a transistor related value. And then you can see that your pole is for beta is right here. So your beta starts to drop at this frequency. FT, which is what we originally set out to find when beta equals 1, going through the math, and this I looked at a few textbooks actually at school yesterday, and all of them had this value for this frequency. But what's interesting is that my math doesn't come out to that. So there's probably I haven't been able to find it, but it just seems like there has to be some algebra, something that I'm missing right here. Because when I take this, okay, if you want to find the magnitude of this, the absolute value of this, when it equals 1, so you want the magnitude of this, which means you multiply this by the complex conjugate, and then take the square root. It means you square it, and if this is the square root of this, but you've got a square root equal to 1, so you can square both sides, and that's what I did here. Took 1 squared equals 1, and then square root of that equals this whole mess. And then you want to get omega t by itself. So I multiplied top and bottom by the denominator here to get rid of the fraction. Then you can move omega t's, so there's 2 omega t terms here. Here's one, here's one. Move them to one side, move everything else to the other side, and then divide out to give you omega t all by itself. And this is what I got no matter how hard I tried. And assuming that R pi times GM is greater than 1, you can assume that this term is bigger than 1. Get rid of that 1, you end up with this. I think maybe this might be the place that I'm making a mistake, because I checked this algebra a bazillion times. And then you end up with this, but the value that textbooks give is this omega t equals GM over C mu times C pi. This is where beta goes to 1, and that's where your frequency is. That is your frequency, your FT frequency, which is your unit current gain frequency, where beta equals 1, FT. Okay, other bits and pieces. Rn for 4 resistor biasing. You may see this in 409. I know Dr. Derrickson used it when he was teaching 409. If somebody says, "Oh, what's the Rn here?" Just follow the signal path. You go through there. Okay, that's going to be 1 over j omega c1. And then since these all go down to virtual ground, all of these are in parallel. Now you go to all paths you hit coming in here. So there's one path up, one path this way, and one path this way. Looking up, you see, well, looking down, you see R4. Looking up, you see R3. Looking into here, you see your R pi plus 1 plus beta R1. Okay. And this is a function. I didn't put in the CBE into here. The CBE would be in parallel with your R pi. And that's why this omega right here, let's mark this as needing fixing. I think we can just fix that as 1 over, I have to check this, so don't 100% trust this. J omega CBE. Are both sides moving? I don't agree with this. So this is a, I'm gonna do a, until I check this, we'll just say R pi is a function of frequency. Okay. So yeah, just follow the path. If it breaks out, then everything's in parallel. Okay, and let's see. C1 gives a very low 0. That's why if you used an AC coupling cap, you will have a 0. Your frequency will go up. Your frequency response graph will look something like this. Then it'll flatten out. Then you get your first pole. Then you get your second pole. Whoops. That's not minus 40 dB per decade. But yeah, the CE will start you out. The CE will start you out with a plus 20 dB per decade increase in your frequency, and then it'll flatten off. Okay, and last metric, gain bandwidth. So here's your Bode plot. Let's say you look at this point. If you find the frequency here, I think you can still see this. If you find the frequency here, and you find the gain here, if you multiply the two, you'll get some number. You'll get some number. So if you multiply the gain times frequency, this is after you've reached this pole here, after you start to drop off. So do the gain times frequency, and that equals some number. And if you pick another point and do the same thing, you'll get the same number. If you pick another point down here, you'll get the same number. And this is called gain bandwidth. Gain bandwidth. Gain bandwidth is equal to constant. Yeah. This is gain bandwidth. Okay. Just any point on here. The gain bandwidth with not metric parameter. I'm not. There's something that comes after this, I can't remember. Ooh, I wish I could erase that. Okay, but anyways, yeah, so gain bandwidth, if you just say the gain bandwidth is, then people know that where this line goes. Knows that you can get a higher frequency at this gain or a lower frequency at this gain. Okay, and one more slide, I think. Again, I've said this before, but cascading amplifiers multiply their gains, and since Bode plots take the log of your gain, that just means if you have log A times B, that means you have log A plus log B, and you can treat the gains of each amplifier separately. Okay, and the end. Okay, all right, thank you. Hope you watched all the way through.